Okay, so the MLE is by definition maximizing the log likelihood, and which is obtained by different. So if you take the partial derivative then and set it to 0, then this is the maximizer will satisfy this equation, right? So that is called the square equation, and to be rigorous, so for the square equation is like tangent. So this the sign of the slope supposed to be decrease. So that's how you need to have this one. But this will be hold for any density function. So now we're gonna move on to an example. So if you first, this is called the Laplace distribution. Is kind of heavy. So you have it's like a zeta, something like this, right? The density function is like this, and and you can actually check minus infinity to infinity e to the x the absolute value of s minus zeta dx is to zeta e to the minus zeta minus x, right, plus zeta to infinity e to the x minus zeta dx. Then this one is minus infinity to 0 e to the minus plus x dx, right? And then this one is to infinity e to the minus x dx. So this is 1 plus 1, 2. So that's why we have a half here. And the maximizing, so maximizer is actually becomes a minimizing this one, right? So how to find the minimizer of this one? Well, basically you one way to, so if you, this is essentially slope, I mean the piecewise linear, right? Piecewise linear function. So so one thing you can call this so this is right, and then if you, what is this? So this one is 1 0 minus 1 if xi is negative, positive. So using that, basically you can see that where you just so if the, okay, sorry, minimizer, right? So set so to suppose you have a odd number like a 5, n equal 5, then you, what is the best way? You have 2 minuses and 2 pluses and 1 0, right? So that will make a 0. So so for even number you don't have an exact 0, but you have a close to 0. So basically by choosing zeta hat to the median of xi, you have half of your data have greater than median and half of your data less than median. So this sine function is add up to 0. So the MLE is median over x1 to xn. Okay. Now let's move on to the next topic. So Bernoulli distribution, the density function is minus x, and so the likelihood function is something like this. So the partial derivative is minus xi, set it to 0, will solve set height equal to 1 over n summation xi. So in the MLE is if there's no restriction on your parameter, then MLE is just this one. And now suppose your parameter space is restricted, then your likelihood function, so this likelihood function takes the form of something like this, right? So suppose whatever the form is, you have a maximum, original maximum is x bar, right? But now if your parameter space is this, so if your this is 1 over third, 0 to 1 over third. So actually, to be rigorous, you don't have any, you have a 0. So if x is 0, then very small number. But so the parameter space between you are not really, so between 0 and 1. But suppose in this case the maximum is achieved, the maximum is here, right? So the maximum, okay, so or you can have 1 over third. So it really depends if x bar, if x bar is, okay, sorry, I better remove this. Okay, sorry about that. Okay, so if x bar is here, then the density function will be something like this, right? So then the maximizer is, so the theta hat is basically between minimum of x bar and 1 over third. So if it is x bar is less than 1 over third, then it's maximum. If it's greater than 1 over 3, then it's actually the maximum. We cannot really use x bar as the MLE because it's outside the same parameter space. So then 1 over 3 is the MLE. Now this is also important property of MLE. So for example, theta, basically if theta MLE is MLE of theta is x bar, then what is the MLE of eta? So theta square, for example. Well, it's very simple. Just the answer is this. Okay. So transformation invariant. So this, given the parameter, given the transformation, the MLE of eta is just a transformation of MLE. Well, if G is 1 to 1, then okay, you are interested in maximizing this, right? But you don't know this. But so question. You can actually, what you have is this one. So fxi theta, right? But you if you have 1 to 1, then you can actually write this way. So you can actually write it as a and now if you view this as a function of eta, right? So this is a likelihood function of eta. So then, but what you know is that you know how to compute the MLE for zeta, right? So zeta hat MLE can be obtained by maximizing this, and so then you have only to apply eta hat. So that means your eta hat is G, so G over eta, zeta hat. So basically the point is you can the point is you can use this one to maximize. So to finding the maximize, you can actually maximize. So maximizing this one, right? Maximizing the likely function of zeta can be viewed for the one-to-one is actually maximizing eta, another function of eta. So you can just you have only to maximize this one, this one, right? This is the likely function, and so that you can obtain by using this relationship. And not one-to-one is it's not really difficult. Not one-to-one. You can just define, right? Define this pre-image. And apply the same argument. So as long as you define, so now this is well defined, then basically you use the likelihood of zeta to obtain zeta hat, and then apply the transformation. Then this is the MLE of eta. Okay.